The last technique we want to discuss in terms of simplifying signals and reducing noise is the derivative operation. And we're going to discuss a very special case of this known as a two-point central difference algorithm. So normally in a derivative, we would take a derivative as a difference. So in a discrete form, you can't really have the typical derivative formula where you have a delta t that's going to 0. So we have the n plus 1th point minus the nth point divided by the sampling time. And so then this gives us essentially the slope between points at n minus 1 and points at n. And this, of course, is done then through the entire record length to give a function of n that's basically the derivative. The difference between the derivative and the two-point central distance difference is that in the two-point central difference, you're not necessarily taking the difference between one point and the previous point, but you're taking the difference between a point and then a point some length of points away, that length being 2L. So you would take the function's value at some point n plus L, subtract the function's value at some point n minus L, and the time between those 2 points is not the sampling time, but it's the sampling time times 2L, where L is sometimes referred to as a skip factor. And in order to do that, we can basically implement this equation with a set of filter coefficients that have non-zero values ranging from minus L to L, and then are 0 everywhere else. So for k minus L to L, B of k, the filter coefficients are 1 over 2LT and minus 1 over 2LT respectively. So basically then, when we take the difference between 2 points and just take a straight derivative operation, so here's an example of a signal. And this particular signal is a vertical eye movement signal, and so what you're really trying to assess here is what kind of how rapidly does the eye transition or respond. So you're interested in this early curvature here. So if we take just the simple derivative, you can see that that appears as this slope and then a lot of noisy signal after that. If we instead take the, and I'm going to get out of the screenshot mode so that you can see a little more clearly so that I can move these figures around because this is not showing up super great. What you're not seeing here is you're not seeing the rise time on this slope on the pure derivative, which you do see here on the two-point central difference algorithm. Now this one has a skip factor of 4. I'll go back to screenshot mode. This one has a skip factor of 4, and you can see there's some considerable smoothing that's done in this peak. So here you could take the length of the peak, and that would basically give you some idea of the rise time associated with the response. So as an example, at looking at what the two-point central difference algorithm magnitude spectrum looks like, we can do that both analytically as well as using MATLAB. So analytically, we would just substitute the equation for B into this sum. And so B, remember, was 1 over 2 L T sub S. And then basically looking at this example, if we group the coefficients, we have effectively the sine function. And so our x sub m becomes basically a sinc function. And L is the skip factor, and n is the number of samples in the waveform. So if we take the magnitude of that, we'll have the magnitude of the sinc function, sine x over x. Oh, I'm sorry, not the sinc function, but just the sine function divided by a constant. So the analytical solution then will end up just being the absolute value of a sinusoidal function whose period is a function of the skip factor. And so we can program that into MATLAB as well. Here's what that might look like. So we've set up a We've set up a sample with 1,000 data points, looking at two different skip factors, a skip factor of 1, a skip factor of 3, and then plotting and labeling the spectrum. So here's what happens if we have a skip factor of 1. Here's what happens if we have a skip factor of 3. Shown here in the figure is this positive slope straight line, which is what would happen if we took a true derivative. A true derivative has just a straight line slope in the frequency domain. Notice that low frequencies, when we do the two-point central difference algorithm, we have the differentiator. At medium frequencies, the behavior begins to change, and then at higher frequencies, we have an integrator. So basically what's happening there is the integrators having the effect of smoothing out the response, while the differentiator is having the effect of determining slope at low frequency. You can see what happens if you now have a skip factor of 3 that gets compressed a little bit, has the integration part act at a little lower frequency. If you were going to do this, you might want to be sure that you don't have any significant frequencies of interest above about 150 or so, and you might want to low pass filter your data before applying this. So basically the two-point central difference algorithm approximates a true derivative at low frequencies, but more of a low pass filter at high frequencies. As you increase the skip factor, you basically lower the frequency range over which you act like a derivative, and you lower the low pass filter range. So for higher skip factors, that response curve is going to repeat itself. And usually you're making the assumption that the signal doesn't contain frequencies in this range. And then, as I said on the last slide, if that's not the case, you would want to use an additional low pass filter to get rid of those derivative enhanced higher frequency components. So there's no real straightforward way to determining the best cutoff frequency or the skip factor. It depends a lot on your data. Most of the time this is either set empirically, usually done through trial and error, just seeing what different filters will do to different types of signals. So the signal bandwidth is progressively reduced until you get some desirable feature of the signal that's lost or compromised, and that tells you to back off a little bit on your filter. So here's an example of looking at a velocity of an eye movement using 4 different skip factors and some data provided by the author called eye data. We're going to look at skip factors of 1, 2, 5, and 10. So here's what the result looks like. And notice that you are getting slightly different values for the velocity of your eye movement depending on what skip factor you select. We're actually decreasing a little bit in that velocity. And so then, based on just sort of an empirical study, the skip factor of 5 gives you pretty good smoothing, but you don't get a great deal of loss. When we go to 10, notice that you're dropping by about 10%. But once again, this is a judgment call and is usually done empirically based on some knowledge of what it is you're actually looking for.